Well, first things first, I'd like to sort of thank you for making yourself present here at LSFA 2021. This is, to be honest, the first time I'm chairing this particular event, and I'm thankful for that because from a regional point of view, it's been a very sort of interesting event. It's typically be held in Brazil, but it's clearly been gaining much more sort of traction, and it's become a pretty important event in the region regarding topics of sort of type theory, lambda calculus, and essentially sort of foundations of formal systems. It's a pretty broad range. So anyway, I just wanted to say I'm thankful for being invited to chair this event. So we'll start off with the first session, which is the invited talk by Alejandro Diaz-Caro. I'm fortunate enough to know Alejandro Diaz-Caro relatively well, because when I was at Quilmes, Universidad Nacional de Quilmes, through projects involving the government, we could sort of help bring Alejandro Diaz back to Argentina from France, so that he can sort of continue his studies in Argentina and start to build up his own research group. So to be honest, to me, it's a great pleasure to be presenting him. He is a researcher at CONICET, which is sort of the top research institution in Argentina. He's also working at the Universidad de Buenos Aires in the Instituto de Ciencias de Computación. We have at Universidad Nacional de Quilmes, he's still, fortunately for that university, which is close to my sort of heart, he is a professor there as well. So, and his areas of research are essentially sort of the logical foundations of quantum computation, involving type theoretical techniques and lambda calculus, among others. So Alejandro Jano, for those of us that know him, thank you for accepting to give us this invited talk, and the floor is now yours.
Okay, thank you for that nice introduction, and for the invitation, of course. So I will share my screen. So do you see my screen?
Yes, we see your screen.
Okay, so what I will do is an overview of this area of quantum control in the lambda calculus. So I will start with some basics about quantum computing very quickly, but we can summarize quantum computing in 4 postulates. So the first postulate is how you represent the state of a quantum system, and one way of representing it is using vectors. So the state vector is just a non-one vector in a Hilbert space, but in our case, what we will use as Hilbert space is only the complex to the power of 2 to the n. Okay, so it's only complex. It doesn't matter what Hilbert space is. This is a Hilbert space, and this is the only Hilbert space that we will care about in this presentation. So in particular, this is just notation, but we usually identify this vector with 0 and this vector with 1, with this notation like this, and then all the vectors alpha, beta will be written in this way, okay? This is alpha times this vector plus beta times this vector, okay? And this is what normally is called a superposition in quantum computing. Why it is called a superposition? Because you can consider that this is a superposition between the bit 0 and the bit 1, okay? But this is, of course, just an analogy. So a qubit is just a vector in C squared, and that's all. And n qubit is a vector in C to the power of 2 to the n. But it's not any vector. The vectors has to be normalized. So the norm of the vector has to be 1, and it will be clear later why. So if I take 2 qubits, I can identify the canonical base with 2 bits. Okay, and then this is a 2 qubits. Okay, and that's all. So it's in the space of the C2D4. The second postulate says, so this is how you represent a quantum state, a particle, the state of a particle. So the second postulate says how the particle can evolve. Okay, so the evolution, how you represent the evolution of the particle, how it changes its state. So in quantum computing, or in this discrete framework, we use unitary matrices to represent the evolution. A unitary matrix is a matrix which is an isometry with respect to the norm L2. So it means it keeps the norm. Okay, so it's a matrix such that it preserves norms. If you multiply the matrix with the vector, you get the same norm as the vector had before. Okay, and this is just the L2 square, the L2 norm. So the evolution of a particle in a given time, you will be represented by this matrix. So if you were in this state, after some time, you will be in this state, which is just the product of these two things. And this is how you represent the evolution. Of course, if you are using continuous time, then there is a differential equation involved, which is the Schrödinger equation, but this is the discretization of that equation. So we need unitary matrices. The third postulate says about the quantum measurement, or how you measure a quantum state. So the quantum measurement is something a bit strange and a bit too much technical details to give in this presentation. So I just give an intuition of this. And the intuition is that when you measure a state, what you are doing is measuring with respect to a base of the space. Or in physics, you are measuring with respect to some particularity that you want to measure of this state. Okay, so mathematically, you say that you measure with respect to a base, and what you are doing is to choose one of the vectors in that base as a result. So if you measure with respect to a base, what you will obtain is one of those vectors in the base, and that's all. And this is all what you recover from the state. This choose is not deterministic. It will be probabilistic. So, for example, if you have these two qubits, so this is just the vector alpha 0, alpha 1, alpha 2, alpha 3, then and you measure with respect to the canonical base, then you will get 0, 0 with probability given by these scalars, the modulus. These are complex, so it's the modulus, the square of the modulus of the scalars. And that is why this has to be of norm 1, because you need that this is, the probability is 1, okay? So if I measure this vector with respect to the canonical base, I get one of these with these probabilities, okay? Again, this is an intuition. It is, you can describe the measurement in a more mathematical way, but this is enough for my talk. So another example, suppose that I want to measure this qubit, which is the qubit 0, with respect to this other base. This is 1 over root of 2 and 1 over root of 2, and this is the same, but with a minus here. Normally, these two qubits are called plus and minus. This is also a base. It's just a base in a perpendicular base. And if I want to measure this with respect to this base, I will get one of these two, of course. And in this case, with probability 1/2, because if I write this vector in this base, I have 1 over root of 2 of this plus 1 over root of 2 of this. So that is basically what we need to know about quantum measurement. And in all the implementations, anyway, in lambda calculus, we use just the canonical base. Why? Because if you want to measure with respect to another base, you can just change bases, change the base, modify the vector, measure, and then modify again. So that is equivalent. So you need only one measurement with respect to the canonical base, and that is enough. So the fourth postulate and the last postulate is the how you compose systems. So if you have several quantum particles, quantum systems, you can consider the full system by doing the tensor product of them. So in this case, for example, if I take the ket 0, the qubit 0 and the qubit 0, I do the tensor product and I get this qubit 0, 0. So in general, if you take these two, the tensor product can be calculated in this way. So it's the first with the second vector and the first scalar here with the second vector. So the tensor product of these two is c to the 4. Okay, and that's all. So we represent the quantum states with a vector. We represent the evolution of a state with a unitary matrix. We measure with respect to a base, which means pick one of the vectors in the base, and which you pick is given by a probability, which is given by the state, because you have to take the scalars. And then the composition is just the tensor product. So that is all what I will say about quantum computing. With this, doing a quantum algorithm is just you define the first state, and then you apply unitary matrices and measurement, and you get the final state. So that is a quantum algorithm. So there is a consequence of these 4 postulates, which is not a postulate, it's just a consequence that you can prove, which is what is called as the no-cloning theorem. The no-cloning theorem says that there is no unitary matrix such that for all vectors and one fixed vector W, you get this. You apply to the composition of these two is, this should be V tensor V, so there is a problem here. So the idea is that you cannot duplicate V, okay? So this should say V here, not W. Sorry about that. So the idea is that there is no way to duplicate an unknown quantum state, okay? So again, this is a V, so V tensor V. So you cannot, from one copy of V that you don't know which vector is, you cannot duplicate it. And you cannot measure to know what vector is, because as I told you, when you measure, you destroy the system. What you get is one vector of the base. So duplication is not possible in quantum computing. This is what this no-cloning theorem says. In fact, it's not that duplication is not possible. Duplication of unknown quantum state is not possible. Of course, if somebody tells you this is my quantum state, then you can create another quantum state in the same state. So that is not a problem. Okay, that's all what I will say about the notion of quantum computing. And so what about quantum programming languages or lambda calculus? So the most used model is what is called quantum data classical control. And the idea is that, as I told you, a quantum algorithm is just you prepare the initial state, you apply some transformations, and you get the final state. So in fact, that control is classical in the sense that you can describe this with this kind of program. You say, okay, prepare the qubit in this state, apply this unitary matrix, then measure with respect to this base. Then if the result of the measure is this, which is one of these in the base, so you can encode it with a bit. Okay, then do that, and else do that. So all the control flow is classic. And this is what you will see, for example, in Seliger and Valiron quantum lambda calculus. And this is the most common and practical and realistic scenario. So when you want to program a quantum computer, you will have a classical computer instructing the computer what to do. So the classical computer will say, okay, apply this, prepare that, and then measure, give me the result of the measurement, and I continue my classical program. But this is the quantum data classical control. What the kind of problems that you have to deal with in the lambda calculus, if you have this classical control, is, for example, the no cloning. So you know that the qubits cannot be cloned, so you cannot, for example, say that you take one qubit and then suddenly you use it in 2 places of your system. You cannot duplicate the qubit. So what they do normally is to take pointers to the qubits, and then you can duplicate the pointer, but there is only one qubit. and or they use a linear type system to ensure that you will not duplicate stuff. And also, there is the problem that was solved by Salinger Valion on higher order of this kind of things. So how you pass a full circuit to another program, and then you have to encapsulate this full circuit, and then if you have some qubits inside, you are not just manipulating the qubit, you are manipulating the program that creates those qubits. So that higher order is managed in this classical control by this lambda calculus. So what we are interested in this talk is the quantum control. Okay, so what does it mean, quantum control? So in fact, quantum control will mean to describe in the lambda calculus what happened at the quantum level. So to describe, for example, the unitary matrices at the quantum at the lambda calculus. And why we would like to do that? Well, in fact, we can go back to the beginnings of quantum physics. And there is a paper by Birkhoff and von Neumann about quantum logic in 1936, so it was the beginning of computing also. Of course, it is there is no Curry Howard with this logic, because this is really in the beginnings of computing also. But what they did was try to see that some of the properties of the quantum properties, like a superposition, are not easily represented in classical logic. So they try to add new connectives and new things to the logic to represent this kind of logic, and that they call quantum logic. There is a lot of work in this quantum logic line, but it is not related with computing. So the intention when we take quantum data and quantum control is to try to create a kind of Curry Howard between a quantum lambda calculus and a quantum logic, not necessarily this created ad hoc by Birkhoff and von Neumann, but any kind of logic. So to understand what is the logic between quantum computing. So the question is, okay, which type system we use, which logic? Okay, that is the question that we want to answer. So we don't have even the logic and the language. We are trying to figure out what will be the language and what will be the logic that we want to see if they are connected. So we want to have a quantum logic which is really motivated by quantum computing, okay, and not just by ad hoc adding to represent some kind of properties, but all. Sorry. Okay, so let me start with this quantum data and quantum control. One of the first papers on this line was by Thorsten Alterkirch and Jonathan Gratas in LEACS 2005, where they introduced QML. It is a language that where you already have some kind of quantum control, in the sense that you can make, for example, you are mixing the program and the quantum data. So you can, for example, do this kind of if, and they call it if circle, or quantum if, where the condition is a quantum state. So the condition is a superposition of 0 and 1. And what you do in this case is you just reduce to the superposition of the two options. Okay, so this is can be think as the first quantum control in the literature in lambda calculus. But of course, if you want to do this, you have to ensure that this guy is also a quantum state. And this is not easy. In fact, this you know that to be a quantum state, you need to preserve the norm 1, because it's not any vector in C2. It has to be a vector that is norm 1. So in this case, you can ensure that the norm is 1 if these two guys are norm 1, if these two guys are orthogonal. So you have to somehow check if these two guys are orthogonal before allowing to construct this term. Okay, and so they managed to do some well-formedness rules with a partial orthogonality checking. They cannot check everything. They can check only in the values if they are orthogonal or not. And then in this QML, you have this kind of quantum control where some programs you can check that they are orthogonal and you can construct it. Some others you cannot. And of course, you can anyway encode all the quantum computing in QML. Okay, so that is enough. But of course, it was just the first attempt, and so we can do much, or we can want to do much better now, and try to see if we can arrive to something else. So this is the first work in the literature, which is a really good result already, and where they introduced this kind of quantum control. Then Pablo Arrighi and Gilles Weck, they in RTA, in fact, they introduced the calculus lineal, or a linear algebraic lambda calculus, as they call it. And the idea was, okay, let's try to see what happens if we mix this kind of superpositions and lambda calculus. So what they say was, okay, let's take the lambda calculus and just allow for create superpositions. Okay, what does it mean? Okay, you have to be able to create linear combination of lambda terms. Just to set the basis to see if we can construct the quantum lambda calculus that we need for this Curry-Howard from there. So they allow a term multiplied by a scalar, a complex number, the sum of two terms, and the null vector. So this calculus is untyped. You have a set of really long set of rewriting rules, which are giving you the canonical form of the vectors. So for example, if you have alpha t plus beta t, then this rewrites to alpha plus beta t. Okay, so they oriented all the axioms of vector spaces so that you have a normalizing, sorry, not a normalizing, so you go to the canonical form. So all the algebraic part is normalizing. Of course, this is untyped, so and this includes all the lambda calculus, so it's not normalizing. And then they have to deal with confluence. So the orientation of these kind of rules, they have to choose it wisely to ensure that the calculus is confluent. And that is this first paper. And to do this, they have to put some restrictions in the rewrite. For example, one interesting example is this. If you take this term that we call delta, so delta is not the classical delta, now is lambda x dot xx plus something. Then you construct the y term with the twice this delta. What you get is that y relates to y plus b, which relates to y plus b, and so on. So this is a kind of infinity in the sense that you can add as much as you want. And if you have algebraic terms and infinity, of course, you have a problem. For example, if you allow infinity minus infinity. And in fact, you have a problem. If you allow infinity minus infinity, you will be able to reduce it either to the vector, the null vector, or to b, or to b plus b, or to whatever. And then you have to impose some kind of restrictions in the rewrite rule. For example, to not be able to do the subtraction unless these two guys are values, okay? Because you have to ensure that they are not infinity, okay? So they managed to add all these kind of restrictions, and they got a confluent rewrite system. And this is, again, lineal, the untyped calculus. So these calculus have some particularities. In particular, you have call by base strategy. This is how we call it now. At that time, they call it call by base, by value. But in fact, the idea of call by base is that is similar to call by value, just that you don't consider a linear combination of values to be a value. This is a base term. And then you cannot just reduce. What you do is you distribute the term with respect to these values, and then you reduce the R. Okay, this is called by base because these two guys are the base of this infinite vector space of terms of values that we have here. Okay, so this is this strategy, and this strategy is great to forbid cloning. So since you are not duplicating the alpha and the beta at any place, you cannot clone a qubit. Okay, so this is the good strategy to not have cloning. But also you can encode unitary matrices. So for example, let's take this unitary matrix. This is 1 over root of 2 in all places with a minus here. This is called Hadamard. Hadamard is the matrix that changed the base 0, 1 to the base plus minus that I showed you before. So it's just a change of basis, but this is a unitary matrix. Okay, you take 0 and it gives you plus, you take 1, it gives you minus. If you take alpha plus 0 plus beta times 1, you get alpha times plus beta times minus. Okay, so this is a unitary matrix. How you can encode it in this calculus? Well, you just can take the 0 and 1 as the usual true and false encoding. And then this Hadamard gate can be encoded in this way. So if this is 0, you get this. If this is 1, you get this one. Okay. And then since you have this call by base, this acts as you expect, which is if you apply it to any vector, it will distribute until it gets to the base, and then you will transform it there. Okay, this is exactly what you expect in algebra. Okay, so this is the calculus lineal. It's great to encode unitary matrices and to forbid cloning. Okay, of course, you can also write vectors that are not quantum vectors here. Okay, so this is a bit too big, but you can encode all the quantum computing without measurement on this calculus. So the next work on this line was a type system for this calculus, which is called vectorial. The vectorial type system is an extension to system F, where we extend the system F in the same way as we extended the terms. So we allow for linear combination of types to be types. Okay, so linear combination of types, it means these are unique types. Okay, sorry, I should use another letter because it is not a unitary matrix. It's a unique type. So the unique type is just the types of system F, except in the right of the arrow. And the general types are either unit type, or you can scale a type, you can add 2 types, and you have a 0 type. Okay, so you are doing exactly the same as you did with the terms. This is, of course, just an intuition. It is not precise. There are some more subtleties on this type system, but this is the important part. And the interesting results here is that you can characterize the weight of terms with these types. So, for example, the weight of values is if you have a linear combination of values, the sum of the scalars is its weight. And for any term, you will say that the weight of the term is the weight of the values it reduced to. This is a strongly normalizing calculus, vectorial. And then the weight of the type is the same as with the values. At the end, everything is a linear combination of unit types. And then this sum is the weight. And the most important result here, or the main theorem, is that if a term has a type, then the weight of the term is the weight of the type. Okay, so you don't have to reduce the term to know the weight. You can check it in the type. Okay, so this is the vectorial type system. We still are planning to do more works on this. For example, there is a question of what is a categorical model of this, on how we can connect this with some logic that we don't know yet. So that are open questions in this line. Another line with this calculus lineal is this other that is called lambda s, which is the idea was to add measurement to lineal. So the measurement happened to be a problem on lineal because this strategy of call by value is great for unitary matrices. As I told you, if you take a unitary matrix and you apply to a vector, you can do exactly this. Just apply this to the base and this to the base, and what you get is the same. And this is exactly what we are doing with the calculus. Okay, so you take this with this vector and then you apply to the base. Okay, so this is great, but the problem is when you want to add a term that measures, or some kind of measurement on this calculus, then suppose that we call this this measurement pi. Okay, pi is the measurement of the term. And then if you want to do, for example, this lambda term that just take an argument and measure it, you cannot use the same strategy, since here you will measuring just the base term, which with probability 1 which give you the same, and here the base term. So this call by value, call by base should say here, this call by base strategy is not great with measurement. Measurement will not do anything here. Okay, you will measure v, since v is a vector of the base, you will get that vector with probability 1, and here the same. So here you will end up with the same vector that you had at the beginning, and this is just an identity. So we need something else. Here we should allow a call by name. Okay, so here we should take the whole vector and then measure it. So somehow we need to move to call by name, but of course we need a call by base for unitary matrices, and then we consider a system where we have both call by base and call by name, and the strategy is based on the type of the variable that the lambda term receives. So in particular, this is the type system for lambda s. So where you have a base term, a basic type, sorry, which is b, the booleans. Then you have arrows. Then you have a product, but you also have this s to mark superpositions. Okay, this is a superposition of this type, and this is just the Cartesian product. Then with this mark of superposition, we can consider that why it doesn't pass. Okay, the two strategies, as I say, based on the type. For example, if the type is not a superposition, for example, this is the base type, then when you apply to this, which is a superposition, you cannot reduce because this x doesn't match with the type of this. You have to distribute in this way, and then you reduce here. Okay, where when these two guys match, then you can do the reduction. So the reduction depends on the type. And if it is expecting a superposition, then you just make the beta reduction there. Okay, but if you expect a superposition, you have to ensure not to duplicate it because of the no cloning theorem. And then we use a linear type system in this case. So the types that are marked with an S are those types that cannot be duplicated. So it's the inverse of the linear logic. It's the inverse of the bank of linear logic. We mark what we don't want to duplicate, okay, because what we are marking are the superpositions, okay, and everything else is a base term, and then you can duplicate it. This Cartesian product is what will help us with the fourth postulate, which is the tensor product. So in particular, this Cartesian product of two terms is just the Cartesian product, but if you do the superposition of that, that is exactly coincide with the tensor product of SA and SB. Okay, so if you do this linear combination, is exactly the tensor product. In fact, the tensor product can be seen as a bilinear, linear in the right and the left, Cartesian product. Okay, so you can do that. And we made a categorical model for this calculus. I have to click twice, sorry for passing the slide. So in this categorical model, what we did was, okay, we take each of the type. The booleans are just the two base vectors that we are interested in. S will be interpreted as a combination of two functors that I will explain in a moment, and the Cartesian product is just the Cartesian product. So what we did was this assumption between the category of set and the category of Beck, where all the interpretation is in set, and we go to Beck only to do the reductions and all the algebraic part, and then we go back to set because the terms are not reducing by themselves. So the S functor is just the span. So if you take a set and you do a span, you get a vector space. And the U functor is just the forgetful functor. So if you take a vector space, you do U, and you get the set of vectors of this vector space, but without the properties. And for the functions, for the linear maps that you have in Beck, the forgetful functor just forget that it was a linear map. It's just use it as a map. Okay. So this assumption allows you to move from a set where we interpret our terms, go to Beck and go back to set. And this is somehow the dual of what you have of some interpretation of linear logic, where normally you interpret everything in Beck and you go to set and go back. Okay, so there is a kind of duality here, and it is normal because we are marking what is a superposition, and we are interested in the base terms. So these are the two natural transformations. The tensor of these two guys is, as I told you, just the span of the Cartesian product. And if you get the Cartesian product of two set of vectors, which were vector spaces before, okay, you just do the Cartesian product and then you forget that it was a vector space. Okay, moving on. The next problem we had to deal with was how to restrict this calculus to be to ensure that what we are writing are unitary maps, okay? Because we wanted to describe quantum computing, and then if you take one map like this one, like if the constant function 0, this is not unitary. For example, if you apply this to this superposition, suppose that this is a qubit, so it has norm 1, then what you get after applying this is 0 and 0 here, which is this, and this has another norm, okay? The square of the modulus of the sum of these two is not the same as if I take the modulus of this and square it. Okay, so the norm is changed. So of course, this is not a unitary function. So we have somehow to ensure that all the functions that we will write, at least those of the right type, are unitary maps. So we used reusability to do this in this paper from 2019, and reusability came to a rescue because what we can do with this technique is the following. We first choose the language. In our case, it was lineal, well, with some changes, but it was morally lineal. We define the types. So suppose these are the types. It is written differently in this paper, but I want to follow my presentation. So let's say these are the types, which are the same as in lambda S. Then you define the semantics. So you say, okay, this should be B, no U. So you say that the semantic of B is just 0 and 1. Then the semantic of SA is the span of A, but intersected with the vectors of norm 1. So you don't take the full vector space, you take just the qubits, okay? So you are making the semantics before you define the type system. In fact, you just define what is the syntax of the types, then you define the semantics, and then you define the type system, but the type system is defined in this way. You say that this sequence is valid if and only if this term reduces to a value which is in the semantic of the type, okay? So what you are doing is the other way around to the soundness. Normally you create the type system and then you define the semantics and then you check that it match. Here we are defining the type system in terms of what is the semantics, okay? So these are theorems, of course. You are saying that this is this theorem, okay? So all the type system is defined, is forced to the semantics that you want. And then, of course, you get this really nice result that is what we wanted, that if you take, this is C square, no? It's the span of the bits. So this is, if you take a qubit, a function that goes from qubit to qubits, then it is a unitary map, okay? So you can force it with these techniques of realizability. So the problem, of course, is that, the problem, of course, is that these realizability techniques will give you potentially infinite number of typing rules. Each typing rule, like this one from this, I derive this, is valid if I say, okay, this by definition is this guy, okay, T reduces to B, which is in A, and this by definition is this, that R reduces to W in B. So if you can prove that from this you obtain this, then this is a valid typing rule. So it's a theorem, okay? So the typing rule are theorems, and of course you can prove as many theorems as you want. So the type system is not fixed. You say, okay, here you have a bunch of rules that works well with this, and you can prove that those rules are valid, but you don't know, for example, if those are all the rules that you need. You know that the system is strongly normalizing because by definition, it is strongly normalizing. You say this is valid only if this reduces to a value which is in the system, so it is strongly normalizing. You have social reduction also, you have confluence, you have all the properties as axioms, but what you don't have is a fixed type system. Okay, so the fixed type system, you have to search for it. And then this is what we did in this new paper with Octavio Malherbe, where we fixed a type system. We extracted this that we call lambda S1, because now lambda S1 is a fixed type system, is similar to lambda S, but where you have only qubits, okay, not anything as you had in lambda S. But of course, we have to define some orthogonality conditions for the typing rules. So those orthogonality conditions in this realizability paper were not a problem, because you just say, okay, if these two are orthogonal, if when they reduce, the values are orthogonal. But if you want to have this orthogonality condition in a type system, it's kind of strange that the type system asks you to reduce the term before typing it. I mean, you don't need a type system if you do that. So we had to use this idea of QML that I showed you before, the first system in quantum control, where you have a partial checking of orthogonality. You cannot check orthogonality for all the terms. You can check for some of them, which is enough for having a system where you can encode all the quantum computing. So this lambda S1 is quite complete in that sense. And we have also a categorical model, which is quite similar to that of lambda S, okay, with some modifications, because now you don't have the whole set and the whole vector spaces. You have the space of qubits, which is not a space. In fact, you have the qubits restricted to those non-1. Okay, so, but the model is quite similar to the lambda S categorical model. So this is what we got coming from trying to define what is the right system with the right type system that we have to represent quantum computing. Then we can check what is the connection with logic, since we have this duality of the S, which is kind of dual of the bang in linear logic. We have some connections with logic, with the logic there, with the linear logic, but it's not clear yet. We didn't prove it yet that we have a dual of linear logic, for example. We know that we can type things that cannot be typed in a dual of linear logic, for example. So it's not exactly linear logic. We have to figure out what is it yet. But another path that we are taking is coming from the other side, coming from the logic, try to see, okay, what we will need to represent a logic, a quantum logic, and then from there, see if we can come to a language. Okay, so we are coming from the other path. And for this, we have this, this first work, which has been recently accepted in ICTAC for this year, which is we added a new connective in natural deduction, okay, to represent quantum superposition. We call it SUP, this new connective. And with this connective, we can represent the quantum computing also. So again, we started from the logic, and from there, we go to a proof system that can represent quantum programs. So the idea here was first to consider this, what is called the harmony principle in natural deduction. So the idea of this principle is that the introduction of a rule of a connective demands as hypothesis the same things that you need in the elimination rule. So for example, if I take the conjunction asks me for A and B, and then you make the conjunction. And this is the generalized elimination rule, where you see that to produce C, you need A and B. A and B were exactly those that were demanded in the introduction. So the introduction asks for two hypotheses that the elimination uses, okay? And then you can do the cut elimination here, but saying, okay, if you do an introduction and then an elimination, you can just take this P3, and each time that you need A, you just take the derivation of A. Each time you need B, you take the derivation of B. Okay, so you have this kind of things if the this connective is harmonic. Another example, for example, is the OR, okay, the disjunction. So, for example, this is one of the introduction of disjunction, where from A you get A or B. And then the elimination, this general elimination, is if you have A or B, you say, okay, I can produce A just asking for A, and I can produce C just asking for B. Okay, then from there you produce C. And then if you have this derivation, you can do the cut elimination by saying, oh, okay, here, since I use A and I have here a derivation that use A, you just change the use of A by this derivation, okay? So this is what is harmonic. Again, what you asked here is what you demand in this, to produce the C in the cut elimination. But you can also consider an example of what is not harmonic. So for example, this is one of the first definition of what is harmonic, and the examples. This is a paper, a 2 pages paper by Prior in the 60s, which where he introduces the Tonk connective, which is not harmonic. And Tonk have the same introduction as the disjunction, okay? From A, you derive A Tonk B, but the elimination is not the same as the disjunction. You only ask for B to produce C. Of course, since B were not one of my hypotheses, I cannot cut eliminate this this connective. So this connective is wrong in some sense, and then that is where he speaks about the harmonic connectives and why we need the connectives to be harmonic. Okay, and so I'm going quite late, I think, so I will try to go fast. So this, as I say, you are not asking this in the elimination. So this is not harmonic. But you can consider other kinds of disharmony. For example, if I take this, our soup, this has the introduction of the conjunction and the elimination of the disjunction. This is not harmonic neither, okay? Because to produce C, you only need A or B, and here you are demanding much more. You are demanding both. But here, in fact, what you will have if you do a cut elimination like this is a non-deterministic rule. You will be able to either produce C by taking this derivation and replacing A by P1, or this derivation and replacing B by P2. So you don't have one choice, and this is because it is not harmonious. Okay, so you have, but the difference with the tongue is that you don't have one choice, you have too many choices. Okay, so in the other one, you didn't have any choice. So these too many choices, in fact, are quite great, because maybe, when I say maybe, yes, we can encode the measurement using this kind of symbol. So first of all, we say, okay, from this you have these two possibilities, and then we could add also something like this kind of rule, a parallel rule, which is not something that you have normally in natural deduction, but you can say, okay, if you have two proofs of A, then you have a proof of A. And then you can keep both of these two reductions by taking the parallel. Okay, you say, okay, you take one, you take the other, and then you do the parallel, and then this is another possible reduction for this. And this is what will allow us to encode quantum computing. And the sub will be what we will use for superposition, where this will be the measurement, and this will be used for the unitary matrices. So first of all, what we did was to introduce a proof language, proof terms for this logic. So it is called the sup calculus, where the sup type is another kind of pair. Remember that the introduction is the same as the introduction of the pairs, the conjunction, and the elimination. You have two. Okay, this is the elimination of the conjunction. This is the disjunction. These two are for the sup. So you have one which is not deterministic. So if you have this kind of thing, you either go to one branch or the other, and the other, which is the parallel, which gives you this parallel term. And then you have all the commutation between parallel and all the rest of the calculus. Okay, so with this subcalculus, this is a calculus for this logic, okay, with this subconnective, and we were able to produce a quantum lambda calculus by quantifying this non-determinism that we have. So instead of taking this previous calculus, we just take this kind of ponderated terms. In the logic, we don't change anything. We just say that if T has type A, then A times T has type A. And then we introduce this only for the parallel and the plus. Okay, these two guys are the ones that can be ponderated. And then these reductions, these two non-deterministic reduction, now you can make it a probabilistic reduction by taking, for example, asking T and U to be values and saying that this reduces to this with probability, I don't know, the modulus of the square of A, and to this, the modulus of the square of B. So you can define as you wish, and this is transparent to the system. I mean, you are not changing much the system, you just quantify the non-determinism. And with this quantification of the non-determinism, we were able to encode quantum computing. So what we have now is that in this calculus, we have the OR, as usual, is what allows you to construct the bits. So 0 is in L, 1 is in R. But you also have the sub to construct the quantum bits. So subtop will be a quantum bit. So this quantum bit is expressed in this sub C calculus in this way. So this, remember that this is a kind of pair. This is a plus, but it's not commutative, not associative, it's just a pair. So here is the pair alpha beta, which is just the vector that we were representing here. Okay, so this is just a pair, but you have this superposition. When you have this superposition, the way to eliminate it is either you take the parallel, which is another kind of superposition, or you do it non-deterministically, like in the measurement. So if you have 2 qubits, then you have the superposition of superpositions. And then here we were able to encode a measurement with this elimination sup and the unitary maps with this another elimination. The details are in the paper. Of course, I cannot give you much more details, but it's quite a easy way to encode it. So summarizing, and with some ideas of future work of these 3 lines I told you now. So in the vectorial line, we still have to make a categorical interpretation and to see what are the connections with logic, this linear combination of types, what does it mean? In the lambda S line, we still need a static orthogonality check, but we did it with lambda S1, but with lambda S1, we are not checking for all the terms, just a subset, which is enough for quantum computing, but it will be nice to figure out how to do better. And in this subcalculus, we are working in 2 lines. One is to see what is this sub connective in sequent calculus, and trying to figure out a categorical model for this, which is not an easy thing. And one idea for future work is not to use this handwritten slides. That, sorry, I didn't have too much time to make it. So that's all.
Thank you, Jano, for your presentation. To be honest, I actually liked the use of handwritten sort of notes. So anyway, so I think we can thank the speaker. I'm seeing some sort of virtual sort of hand clapping going on. So thank you very much. And then I'd like to open the floor for questions. So please let me know if you have a question. Elaine, thank you. I think Christian creo que le tenés que permitir.
Yeah, it's already.
Yeah, okay. Gracias.
Yeah, I could unmute myself.
Good,
Hi, Alejandro. Thank you. It was wonderful. I mean, a lot of things, right? I mean, it's impressive the amount of work that you've done in lots of different directions. And I was going to ask you about the connection with linear logic and when you talked about semantics, but you already told that, so no need for that. I only want to make a comment on your new connective. So first of all, I read the paper. It's really nice. Of course, I did not understand the second part very much, but your presentation today was, gave me some glimpses of things that I couldn't understand before. I think that it's not complicated at all. Actually, I did some, sanity checks myself when I read your paper in natural reduction. I tried to make the sequence calculus out of it, because I can reason about sequence calculus and natural reduction. For me, it's more complicated. I think this is not going to be a problem. When you talk about a categorical model, however, then I have my doubts, because although you have normalization, so you're going to have contamination and everything, it's not clear to me how you're going to glue together the proofs, when you do the substitution and normalization. So yeah, so it's just a comment. So do you have any ideas on that? I mean, have you thought a little bit about that, or?
We have been working the last 3 months with Octavio Malherbe from Uruguay, who is a categorician guy, trying to figure out a categorical model for this, and all our attempts were failed, but we are still trying to do it. We have some ideas, but of course that since you have probabilistic calculus, so it becomes quite hard very easily, because you need one monad to control these probabilistic results, another monad for the parallel, because this parallel composition is not the probabilistic results, is something else. So you need 2 monads, which I I wanted to go back and I went to, anyway, okay. It's the first time I do a presentation in PowerPoint, sorry. And now we have to go back to there. Okay, so the thing is this, I will arrive at some point. These two constructions are quite similar in the categorical sense, but they are not the same. I will not arrive. I think we will go to a break and I will arrive to my slide. But anyway, so these two constructions are quite similar here. These two constructions, which is the parallel, the non-deterministic one, and the parallel one, are quite similar in the interpretation, in the categorical interpretation, but they are not the same. And their interaction is quite a lot to take care of. And that is what we are trying to figure out. We are using multisets, but two levels of multiset that are not the same kind of multisets, so two colors of multisets, and the interaction is a mess. So it's not easy. We have been working for 3 months, and each time we say, oh no, this doesn't work here, and then we have to go back. And at some point, I hope we will figure out what is the right categorical interpretation. In sequent calculus, we are working with Gilles Deweg and with Jean-Baptiste Joannet, who is okay, the guy for that we know in sequent calculus, so he helped us a lot, and we are the three of us working and trying to produce something, and I think we will produce something soon. As you say, is quite it's not that indirect. I mean, it's quite direct. You can do it somehow.
Thank you, Elaine, for the question, and Jano for your reply. I think we have to move on to the next talk, if I'm correct.
I will promote the use of Clowder, since I have been doing this all the week. So Rafael put a link to Clowder. So during the break, I will be there if you have any more questions to ask. Thank you.
Thank you, Jano, and once again for your talk.